Okay.
Hey everyone, how's it going? Can you see? Yeah.
Okay, let's start. So yesterday was very theoretical. Today is much more practical, but also important and not so easy. But I think that has nothing to do with Haskell. That's in general a general problem. But Haskell actually has very nice ways to deal with concurrency that are also unusual and quite unique to Haskell, I think. So today is about concurrency, and we will see some first networking examples. So the goals is to show how to do multi-threaded programming on Haskell, where the most fundamental primitive is called fork IO. Have a simple example server, and then talk about shared memory, and in particular about software transactional memory, which is this unique thing that Haskell offers. And first, a few remarks about the difference between concurrency and parallelism. So concurrency is a language construct that supports structuring a program as if it had many independent threads of control, which does not necessarily mean that it really runs those threads in parallel. So even on a single threaded process, you can switch between these, virtual threads basically, so it looks as if it has different threads. And that necessarily involves some side effects, so we will be in I/O, and it's independent of multi-core. So even before there were multi-core processors, you could have concurrency. And it can be used to implement parallelism, but it's not the only way to do so. And parallelism is running parts of your programs in parallel on multiple cores or nodes in order to speed up the program. So that has a different goal. It's about speeding up things by doing work in parallel, whereas concurrency is more, to be able to do multiple things at once, even if it's not in parallel. Like in a UI, typically you don't want the UI to freeze while some computations are happening. And there it's more about speed, and it only makes sense with multiple cores if you really can do work in parallel, because there's of course also an overhead with this context switching. And conceptually it doesn't require side effects, and in fact it's even better if the results are deterministic. So in this course we are not talking about parallelism, but Haskell actually has ways to do like pure parallelism. So you don't need I/O. And then you get deterministic results. And so we only talk about concurrency. And as an example, using a simple or implementing a simple server. So let's start with concurrency. And let's start with, does everybody has a laptop? Yes, so maybe we can start with this mini exercise. So implement a simple function that given an int returns an IO action which will forever print that number onto the console once per line. So your task is to implement this number forever. It takes an int, then some return type that you can figure out. And if I execute that, for example, in GHCI, with the argument 42, then the behavior should be that forever it will print 42 on the console. So maybe you can try to do that in 5 minutes until 3:05.
People that are watching can write like to the Discord privately, so we can check the results.
So this is really very simple. It's like a one-liner or two-liner. Sorry? Yes, now. Okay. Yes. I just want to write the header. Just a second. Okay, can somebody suggest what to write? Sorry? Do? Okay, do is good. Maybe, yeah. Print n, yeah, okay.
And recursively call number forever.
Uh-huh, yeah.
And yes.
And what is the return type?
IO brackets.
That would work. Right. I think that would work. Let's. Okay, so that's correct. Two remarks. First of all, because this thing never returns, we can give it a polymorphic return type. That indicates, I mentioned that briefly yesterday when I talked about forever, that because it, so basically this return type, I mean, the only way to get something of a polymorphic return type is if it's loops. So this signature would give a hint to somebody using the function that it will never return. But the unit is also correct. It's just more special, specialized. And we said earlier one should normally strive for the most general signature. And secondly, I mean, this is perfectly fine, but of course we have to repeat this n, so probably I would do something like this. Or this, I mean, if you prefer do notation, you can of course also write it like this. But this is a case where maybe, because it's so simple, people might prefer using the then operator. And finally, yesterday we learned this forever. So one can also simply do forever print n, which is probably the shortest solution. Why doesn't it work? Okay, because I need to import control monad. Right. So, I mean, lots of solutions for that, and yours was, of course, correct. We reload. Okay. Right, so now that we have that, let's talk about threads and concurrency. So we can import control concurrent, and then there is an important primitive, so it gets an IO action. It's called fork IO. It gives an IO action and it immediately returns, and the result is a thread ID, but the side effect is that it will run this given IO action in a new thread. And this thread ID is just an abstract type that normally one doesn't need, but it's like a handle on the thread. For example, you can kill that thread if you have the handle. And this thread is not an operating system thread, it's a Haskell thread, so it's built into the Haskell runtime. And they are extremely lightweight, much cheaper than, operating level threads, which means you can have hundreds or thousands of them running in parallel without it becoming a problem. So, and there are, in the Haskell runtime system, there are two options. So the one we have been using by default until now is the simpler one, and it will ever only use a single operating system thread. But you could still use this fork IO, but then it will nothing will be in parallel. It will switch between these different Haskell threads then. Or you can use a more complex version of the Haskell runtime if you pass this parameter -threaded to GHC, and then you can actually use several operating system threads if you have more than one core. But from the point of view of the programmer, fork IO just works fine. It's just if you use the threaded, then potentially the Haskell runtime can use more than one operating system threads on different cores. So just see what this thread is. This is a bit, okay, we could do that, but let me just do it like this. So let's just start with, okay, let's create an executable. So what I call it. I have in the Cabal file for today, I already prepared 2 executables, but let's just do another one. And I don't know what to call it, number forever or whatever. Don't need this. And here in this example, I now have given some flags to GHC. So in particular, this threaded, our valve to display all warnings. This O2, I just always use that for executables. That's the optimization. So I think O1 is without optimization. That's the default. And O2 optimizes. So that can sometimes be quite dramatic, the effect. There's also O3, but I think that is a bit more experimental. So that can be even more. So O2 is like a good choice. And then finally, this -RTS ops means runtime system options. So that means if you build an executable, you can pass these special options to GHC basically. So you can execute your program with various options. And one of those options is -N, which means that it will try to use all the cores on your system. So, okay, this number forever doesn't exist yet. So let's add it. Number forever. Oh yeah, and one more thing, because I now defined this number forever function in the concurrency module as a dependency. I depend on this concurrency module. Just a second. Probably a bad name, but anyway. Close this for the time being. This as well. So, okay. We just build. I should get an error that there's no main function. Yeah. In the main module, we always need this main function, as we know. Okay. And let me import this concurrency number forever, that we can use it. Okay, and now I can see. So, okay. IO number forever 1 to 10. Okay, fork IO, for that I need to import control concurrent, as is mentioned on the slides. On the slides there's this thread 0, which is defined on the next slide, and it forever does this. Okay, fine, maybe I should also import that. So it's a bit, it should be defined before. So it prints, so it's similar to this number forever. The only difference is that it waits. So let's one step at a time. So we have seen how to fork threads. Actually, thread 0 is equivalent to number forever, I think. No, sorry. It's not. Okay, so let's implement it. So first of all, second, so I just defined it as 1 million. And so there is in control concurrent as well as this function thread delay. So that takes an int and then delays the thread in which you call that function or this IO action for the given number of microseconds. So if you say thread delay 1 million, then your thread will sleep for 1 second. So let's do this thing, thread into thread n forever. So it's very simple, similar to your number forever. The only thing is that in the number forever there is no delay. So now we also delay. So we print the number and then we do thread delay. Seconds. Diff 10 to wait for a second. They must import thread delay as well. Okay, now we have this. Now let's go back to our executable. So there was thread 0. Right, now I can try this. So, but maybe before I should explain. So what is that supposed to do? We learned map m underscore yesterday, so that maps a given function over a list, but the function is like is a monadic function, effectful function. And the underscore means we are not interested in the results. So this fork IO gives, as I said before, the thread ID, but we are not interested in the thread ID. So for all the numbers from 1 to 10, what will this do? It will fork a new thread that will execute this number forever function that you implemented in this new thread. So we will fork 10 threads. The first one will forever print 1, the second one forever print 2, until the 10th one that will forever print 10. And then in the main thread, we call this thread 0 function, which is very similar. The only difference is it will not just print 0 forever. It will, between each print, it will wait for a tenth of a second. Right, let's try whether this actually works. So I can try it from GHCI, but then I have to say, because now I have, so I called it number forever. Okay, so let's see what happens if I type main. Okay. So it's going. And if I now press Ctrl, and we see that we get like garbled output, but let me Control C, try. Great, doesn't work. Let me just, normally I should be able to stop it with Control C. Maybe I just close this terminal and switch to a terminal. Still going. Can I somehow? J?
Yes.
Uh-uh.
To gain the access path.
Nope. I mean, in the past I was always able to control C.
Me too.
Ah, control D. Control D did the trick. For whatever. Okay, right. So yeah, it's very confusing. First thing to note is that when I finally killed this, or let me just do it without GHCI, because sometimes GHCI behaves differently to, so let me do cabal run number forever. I mean, it isn't executable. Okay, and this looks better, so somehow. But now Control C also works. Right. So we see that the numbers from 1 to 10, and there should be zeros in between as well, but less zeros, because with the zeros I always wait for a tenth of a second. Right. So we see it works, sort of. So these things happen, these 11 threads now, the main thread, and the 10 that I forked do their thing like simultaneously. And about lifetime of the threads, so the thread gets, I mean, all forked threads get killed when the main thread gets killed. Which in the case of GHCI is GHCI itself. And in the case of like when I call it as an executable, then when that executable stops, then all the threads also stop automatically. They're killed. Okay, so that's basically the basics, how you can do, how you can fork different threads. And it's non-deterministic. So I mean, I start them in this order. So if you look again at the output, so I started them in this order. So one should expect that, I mean, it's always, what we see on the screen is always 1, 2, 3, 4, 5, 6, 7, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But we see it's not. I mean, then the ordering is garbled somehow. So it's not guaranteed that they like stay in the order in which I forked them. So it's, I mean, it should be relatively fair that they each get the same amount of time to do their thing, but it's not completely deterministic. And all threads are killed if the main thread is killed. And in GHCI, the main thread is the thread running GHCI itself. So in order to stop it there, I must close or kill GHCI in order to stop everything. Okay, this we had. Now this is a slight variation, so I can do this as well. Let me modify the main function. So now instead of typo. So this is so just instead of number forever, it uses thread. So the only difference is that there's this 1/10 of a second delay, and then in the main thread here, I just do a thread delay of 5 seconds. I don't need this number forever any longer. And let's try this out again. Maybe clear the screen. A bit bigger. So I run it now. And after 5 seconds, it should stop. Yeah. So similar, only not as many numbers, because now every thread only prints a number every 10th of a second. So if we look at the code again, so here again, I fork these 10 threads. So they now run independently and print their number on the screen every 10th of a second. And in the main thread, after I forked, I wait for 5 seconds, and then the main program ends. And because if the main thread is killed, every other thread is also killed, everything stops, so the others also stop. And waiting is not hot waiting, so it doesn't consume any resources. It basically just yields control of that thread for that amount of time. So waiting is harmless. Okay. So are there any questions at this point?
Don't make the execution more predictable.
I mean, you can, as we will see later today, I mean, there are ways to communicate between threads. So, I mean, then you need to somehow communicate and synchronize. But if you just fork and they are independent of each other and don't talk to each other, then no, I think. So this is, of course, an important point. I mean, but we will see now in the next section that even if the threads are completely independent, it's already useful. For example, you can do something like a server. So are there any other questions? Okay. And let's talk about networking a bit. Right. So I just show you the, I mean, I have implemented this already. We'll make it. Okay. Right. So for this example and in future for this course, when we do like networking, we use a library called Network Simple, and that's on Hackage. I'll make it bigger in a second. Right, so that's called Network minus Simple, and it has some relatively simple way to write web servers or network servers and clients. So we want to use this. And this has now nothing to do with internet. I mean with HTTP or with web. I mean, you could implement that, of course, on top of this, but this is now really a bare bone simple server that just, I mean, text or bytes actually. So it can serve bytes and talk to clients exchanging bytes. Okay, and let's see how you do that. So this executable here is the server, and what it's supposed, okay. So first of all, so this is my main program. So that starts basically the server. So the first thing is I start listening at a specific port. So I give the host, which is just the local host, so it's my laptop, and I give the port, just like this, as a string. And then I must provide a continuation function that, given a socket and an address, says what I want to do next once I have opened that port to start listening on it. Right, then I just write a message that I'm listening on whatever, which in my case, I mean, we will see. And now I'm just waiting for incoming connections. So forever I will just wait for somebody who wants to connect and deal with him. And I will do that forever. And in this network simple, there is something called accept fork, which accepts an incoming connection and then forks a new thread to deal with it. So that means this accept fork will immediately return. So simultaneously, hundreds or thousands of clients could connect to my server. So this just creates a new fork and forgets about it and then waits for the next client. Okay, and now this accept fork takes as first argument the socket that I got here when I started listening, and then takes a continuation which takes another socket. This is now the socket I use to communicate with this specific client that has connected, and the client's address. And I just print an informational message that I accepted the new client. And now I could just work with the socket. So once you have a socket, you can send to the socket and receive from the socket, and that's probably also what you should do. However, to make it simpler for you, and also because in the past we used handles, we decided to, in this lecture, in this course at least, instead of dealing with sockets directly, use handles that we talked about when we talked about files. So remember, I mean, files, you can open a file. There's this with file that we talked about where you get a handle. So you can use these handle-based I/O commands to write to a file and read from a file, or write to a handle and read from a handle. And so until now we have talked about standard in and standard out and file handles. And there's also now basically network handles. So given a socket, there is a function in the network package, which is a different one, but it's basically one that this network simple wraps. So there is network here, so another one. So that is more low level. Sorry, now I did it twice, I think. Let's go back to network simple. So this network is more low level and gives you more control. So we in general want to use this network simple, but we need this one function socket to handle from network. So given a socket and an I/O mode that we also already talked about, it gives me a handle. And then I can just use the handle-based functions that we have already talked about. hGetLine to read a line from a handle, hPutStringLine to write a line to a handle. So this is called the, at least in this course, it's called the standard server pattern. So, I mean, so far, this would basically be the same for every server you want to write, because I haven't said yet what you actually do once a client has connected. So you start listening on a port, and then you have this forever loop that just accepts connections and forks their handling in a new thread. And then you, I mean, what you now want to specifically do, I wrote it as in another function. So this is now for one specific client that has connected, and we have created this handle to talk to him. And in this specific case, what I do is, so the server, first of all, for this to work, you must set the buffering of the handle to line. And then forever, I mean, in this specific case, so the server waits for a line of text from the client, and then converts it to all uppercase and writes it back to the client. So this is the first very simple example of a fully functional server written in Haskell, and we can try it out. So if all goes well, that should, I mean, once the server is running, I should be able to connect to it, and then I can give it lines, and it should shout them back to me in uppercase. So let's see. First of all, I started with cabal run. I called the executable shouting server. Okay, and I get this. I mean, because I'm running it from a container, it just tells me that it forwarded this port, so it's also available on my machine outside the container. And this is this message that we got, I mean, that I wrote here. Start listening on the port. So the server is now available on this port. And in principle, I mean, probably firewall and whatever, but in principle, you could now connect. I mean, if you knew my IP address, you could connect to this server and interact with it. But let's, I mean, I first do it on my machine. So I could do it here from Visual Studio, but I can also do it just from my console. So let me just make it bigger. So this is now outside the container. And so now I just need some way to talk to a server. And I mean, I'm on Linux, and there is a standard tool called netcat NC. So I just tell it the address and the port I want to connect to. I mean, this has now nothing to do with Haskell. The point is that the server is a proper server. I mean, just a server. It's implemented in Haskell, but it's a server. So I can use standard tools to talk to that server. And netcat is one of those. So, okay. Now let me switch back to Visual Studio. And we see this debug message there. Accepted client, blah, blah, blah. So it seems I'm now talking, I mean, I connect, that's now the netcat. And so we are now, let me just go in the code. So this is now comes from this line here. So now we are here in handle client. The server is now waiting to read a line from the client. So let me switch back to the client and do a line. Hi, how are you? And when I press enter, this netcat tool will send the string that I entered to the server. When I do that, I immediately get a reply from the server where it's in all caps. So now the server read this line and immediately, using the same handle, wrote the all uppercase line back. And now I can do this again. So this works, and I can also open another tab, and it always takes, for some reason, takes a while. Okay, let's do this from this tab as well. Okay, so this also works, and if I switch between these two, so they are both connected now. If I look here, I just get this message, another client connected. So the server is a proper server that can handle simultaneously many clients. And so now people could connect, and the server would just do this simple thing, throwing back whatever they receive from the client in all uppercase, which of course is just an example. Now if I go back to one of these clients here and exit netcat, so then if I look what the server says, then we do get an exception there, because now so that comes from this line, because now the client closed the connection. So when I try to get a line, it gives an exception. And that will kill this thread. But what we see here, if I go back and say, so this I killed, but if I go to this one and say, whatever, Nairobi, so we see the server is still working. So what's happening is this thread got killed, the one dealing with this first client, because of the exception. But when a forked thread is killed, that doesn't mean that the main thread, the thread that forked them, also gets killed. So if you want to do that, there are ways to achieve that, but by default it doesn't. So that means, my server is happily going on, and also the other thread that was dealing with the second client is happily still working. Only the one where I closed the connection crashed. Yeah, so it's quite robust. So people can connect and disconnect. Of course, this is a little bit ugly, so I could try to catch that exception, but it doesn't do any harm, so it works. So simultaneously, people can connect to this server and interact with it, and disconnect again, and it's all good.
So what's the limit? You say threads are hustler threads, not listener threads.
Mm-hmm.
So if in a production setting,
Mm-hmm.
how often one could be, what would be the maximum?
It of course depends on the load that they do and on how many cores you have, because now I set this threaded, so it end with RTS ops minus n, so it's using my cores. I think I have 16 or 16. But in the documentation of Network Simple, somewhere they say 2048 is a good default. So something in that order of magnitude, definitely that 2,000 people could connect to it simultaneously. And of course, if you want to run in production with millions of clients that connect, then you need something like different, like load balancing and.
Maybe the network package that gives you more control and will allow you to.
Of the other stuff.
Mm-hmm.
Yes.
This
is a wrapper. Yes.
I just want. I think. I haven't used this library before often, or never actually. I think, but the way I understand it is, except fork, basically keeps count of how many clients are connected. And there they recommended this to use this 2048. So I think if now more than 2048 clients, I mean, if a 2049th client tries to connect, it would just not accept the connection. So, but that you can configure that.
Parameter, yeah.
Yeah, so it's basically protecting itself that it doesn't get too many, I mean, like a denial of service attack or something. So that would already, yes.
It also has a limit for the size of the messages as well.
Right. Yes. Yeah, but I mean, it's right. As you see, it's easy to basically get a very simple server working. And in principle, you could now like do, I don't know what, Google Sheets in, but obviously, if you want to do web pages or stuff, then you wouldn't use such a low-level thing where you just deal with strings. I mean, you would do something else. And later in the course, we will also show how to actually run like a web application. But I mean, the basic thing, I mean, that's what the server is, right? There's some network socket and clients can connect to it and send bytes and receive bytes. And so that's very easy in Haskell to do. And, right, any more questions? And now I use this netcat to connect to it, to my server. But of course, you can also use Haskell to connect to a server. So I also prepared that already. I called it shouting client. So using the same network simple, you can write an executable that will connect to this server. So where the server started with listen to basically bind this port and listen to it, listen for incoming connections, connect is now from the client side and will connect to a given address and port. And as argument, it gets a continuation given a socket. And that's now we do basically the same we did before. So we turn this socket into a handle and then say what we want to do with this handle. So now we can talk to the server via this handle. And in this, I wrote this helper function here, copy by line, which gets two handles. The idea is it reads from the first handle and writes everything it reads from the first handle, it writes to the second handle. So I just forever read from the first handle and immediately write it to the second handle. And now I use this here in my client. So first I fork a thread that uses this helper function to read from the connection I now have to the server. So the H is now my handle to talk to the server and yeah, to talk to the server. So everything I receive from the server, I write to the console. And so this is now in a thread, so that happens like in parallel, concurrently. And then I copy everything that the user types and send it to the server. And we can try that out as well. So the server here is still running. I could do it from here, or I can also do it from my terminal. So let me keep this running. But here, so yeah, run. So this is now called shouting client. Okay. If I go back here, nothing happened. Worries me a bit. Okay, sorry. It was still compiling, or still needs to compile. Yeah, somehow too long. Not sure why this takes so long. Maybe because it needs this network simple or something.
It shouldn't take so long. Maybe the IOG update.
Yeah, I updated my machine just before the course. It was maybe a mistake. I mean, I can do it from the container. From the container, it would work. But it's still responsive. So, okay, let's just let that be. And I just open a new terminal here inside the container. And try it from here, shouting client. Okay, let's switch back to the server. Okay, are now two connected. So I think by now my other one, yeah, I think this is done now. It took so long because it was connected now. So it didn't take so long. So now, I mean, yeah. So now I'm connected, I think, and now it, with this Haskell tool now, so I can try this again. I am using Haskell. Yeah, and basically we observe the same behavior as we did when using netcat. And on the clients, yeah, and I can also try it here from this other tab in the container, if I manage to get there. This is another tab. Right, so that works as well. So now I have three connected. I still have my second netcat connected. I have this shouting client from here and the shouting client from here. Yeah, and still, I think this one is also still open. So if we disconnect here, disconnect here, disconnect here. Right, and the server is still happily running. So what we see that three now disconnected. Yes, so it's relatively easy to get simple servers in Haskell up and running, and it's also easy to talk to them. I mean, to write a client that talks to a server. Okay, are there any questions? Okay, let's see on the slides whether I forgot anything important. Okay, and this server pattern, so you start listening, and then forever you accept clients and fork a new thread and deal with them in the thread. And as I said, it will fail with an exception when the client disconnects, and then we saw that the default exception handler prints the exception, but only that thread is terminated. So our server kept running even though that thread dealing with that client was killed. Okay, I showed you the client already. Right, so that's basically this. So it's threads 101. And right, so the next topic would be how to communicate between threads. And there are, yeah?
What's the root?
Oh, a good question. As I said, when I talked about fork.io has type, I mean, the return type of fork.io is IO thread ID. So I do get a thread ID back, but I don't want to use that thread ID. And there are several ways to deal with this. So let me just show you, sorry. Yeah. So, I mean, if I didn't have this void, then it would not be an error, but then I would get a warning here. The warning would say a do notation statement discarded a result of type thread ID. So, which says this action here results in a thread ID, but I'm not giving it a name. I mean, I could give it a name, whatever TID, for example. But now it would complain that I'm not using this TID. And one way to deal with that is to do underscore. So now the warnings are away. But this doesn't work if it's the last line, because in a do block, the last line can't use a bind. I mean, it is not the last line because there's this copy by line afterwards, so it would be fine in this case to do it like this. But void, okay, I think it's in control monad as well. So void works actually for every functor, and in particular for I/O or for monads, and takes a computation with the result and turns it into a computation without a result, I mean with unit result. So the implementation, of course, is very simple. I mean, we have functors, so we can fmap, so we just map any result A to unit and fmap this. And then, so we turn an I/O action with a result into one without a result. and the side effects will be the same. So if I use void before I mean like this here has type IO thread ID, but if I apply void to it, then it has type IO unit, and then this warning goes away because now there is no result that I'm ignoring because unit is not interesting. So void is just to, if you're only interested in side effects and not the actual result. And I mean void, I mean it's like in C or Java or whatever, I mean where you have functions of return type void, where you're only interested in in the side effects of the function and they don't return a result. So basically void takes something with a result and turns it into something without a result. So it only forks the thread, but it doesn't give you back the thread ID now. Are there other questions?
What advantages of functional programming would you get when designing servers that you don't get in a JavaScript or
Sorry?
Advantages of using Haskell and functional programming in general versus imperative programming
just in designing servers
to write servers.
Well, I mean, I mean, this is now not functional programming, it's specifically Haskell. I think the Haskell threads are really cool. So I think some of I mean, Warp, for example, is a server written in Haskell, and I think it's one of the fastest out there. So it's faster than other, I mean, but that has nothing to do really with functional programming. It's just because the Haskell runtime is very good with these threads. So it's just very performant. Well, I mean, these handlers, for example, they can be more or less pure functions. I mean, not really, I mean, they do have to talk to, but you can abstract that away. So in principle, you can like write I mean, it's the same advantages you always have with functional programming. I mean, you can write your handlers more or less as pure functions and test them then and so on. So, I mean, it's the usual advantages. And it's typed, I mean, in this case of Haskell, it's strongly typed and so on. I mean, there are libraries. One is, for example, called Servant to write servers in a type-safe way with different endpoints. And there the handlers have, I mean, for example, you basically specify on the type level that whatever you expect query parameters of type int and string and whatever. And then basically the Servant framework allows you to write a handler that then just takes a string and an int and returns something. And so it's very type safe, and you can be sure that your endpoints basically match the handlers and so on. And all the wiring is taken care of, the serialization and extracting the parameters from the URL and encoding it correctly and decoding it and so on. So there.
You can generate the clients?
Yes, and then you can automatically generate the client for it given the API description. And so they are quite powerful once you use this strongly typed way. So basically your API is described as a type, which is some very advanced Haskell, but actually easy to use in the case of Servant. I mean, maybe I could quickly.
Oh, no.
No?
No, I'm just thinking. What did you do?
I'm sure there's a nice example somewhere.
This is more of the advanced type level thing.
Yeah.
Deep functional thing.
Just looking for an example. Maybe a bit better example. For example, here. I mean, so this is what basically a servant description of an API looks like, and you can't understand that now because. But anyway, this is a type. So the API description is a type. So we haven't seen why a string could be a type or anything, but don't worry about it. So but that does basically, I mean, even if you don't understand the Haskell part, you probably do understand what it says. So I mean, there are two endpoints. One is at users/list all, and that's a get method and will return JSON. And the other, and I think enlarged it too much. So it will return a list of users, JSON encoded, and the other one is list all and users, and will also return, is also get and will return a list of users or whatever here. Just looking for example of captures. Or here, for example, this will have two endpoints. One is both are user and then capture, so user slash, then an integer, and it will return a JSON encoded user. And if you use the, right, whatever, or so this is get, and then you also have a delete method to delete that user. And I mean, I think that's very nice. I mean, it's somehow on the type level is relatively easy to understand. And then once you have that type, you can, I mean, write handlers for it. So for example, a handler for this would take an integer and return a user in IO, let's say. So you would just need to write a function from integer to IO user, and the JSON encoding and everything and extracting this integer argument from the URL between the slashes would automatically be taken care of. Or here you would basically write a function from integer to IO unit. So it has no return type, and then in that function you would somehow go to your database and remove that user. But that's not the only thing you can do. So you can do the server this way, but there's also, you can basically with one click of a button, you can generate a client for it. So you could you can use Haskell, for example, to talk to this server, also with the appropriate types then. But you can also generate code, for example, in JavaScript. So it would spit out a text file or JS file with JavaScript code to talk to this specific server. So it would have endpoints for, or method or functions for each of these endpoints. So, and you can automatically generate documentation. So this basically documentation of your server with all the endpoints and the types and examples even and so on. So it's really very cool, I think. Okay, any more questions to the server stuff?
Tomorrow we'll see servers.
Yeah, tomorrow the lecture is more about networking, I think.
Network servers.
Network,
Not,
yeah.
not servers.
Not servant, no. These simple ones. Right. Okay, then if there are no more questions, let's talk about communication between threads. I mean, that was mentioned before, how can you coordinate or synchronize threads? And there are various methods. I mean, in principle, everything you probably know from other programming language, you also can do in Haskell. But there is this one thing that we talk towards the end of the lecture, the software transaction in memory, that's quite unique and very cool. Okay, so the easiest thing is shared memory. So some memory that all threads have access to and can mutate. And it's convenient, especially if you have large amounts of data, because, I mean, if all threads can see it and edit it, mutate it, then you don't have to copy anything. But of course, it's also risky if two threads simultaneously try to modify the same memory. And an alternative would be message passing. So the threads don't share memory, but they send each other messages. And so that has more overhead, but is less risky. And in principle, in Haskell, you can do both. So there are Haskell libraries for this message passing. And this message passing, for example, is used famously by Erlang, I think, to very successful. So I mean, Ericsson is handling, I don't know, hundreds of millions of phone connections using this message passing style. And they have an insane uptime, 99.999 whatever. But, right, so that's also possible in Haskell, but we talk about at least today, about this shared memory approach, what you can do there. And one of the simplest types in this context is IO-ref. So here's the API. So that's like it's like a mutable variable in Haskell. And mutation is a real-world side effect, therefore all of this is an IO. So there's a type IO-ref, A, which is basically a mutable variable of type A, and can be an arbitrary type, Haskell type A. You can create such a mutable variable with new IORef, and you can read from it with read IORef, and you can write to it with write IORef. So we could try this out. Let me go back to my concurrent.
It says in the slide that the IORF stores event computation. Does that mean when you put something in IORF, it doesn't get...
I can demonstrate that now. Right. So let's import data.ioref. Let's do whatever. Okay, so let's create one. So let's see. So I have this new IORef. So let's create one for integers. Let's call it V. I'm not sure I've shown that yet, so maybe I have. So in the GHDI, you basically can also use like do notation. So if I have, this type of new IORef, so I want to do whatever, IORef 42, type int. So if I do this, then the return type will be, it will be an IO action, GHDI will execute it, and I will get one of these references as a result. And if I want to give that a name, in code, in a do block, I would do name and then this arrow. And in GHDI, I can also do it like this. So if I now press enter, GHDI will execute this IO action and will bind the result to the name V. So now V is of type IORef int. So it's a mutable, it's a reference cell, a mutable variable. A cell that contains an int, and that int can be read and written to. So at the moment it should be 42, because that's how I initialized it. So if I now do read IORef, my V, then I get 42. But now I can also write to it. So it gets, the cell I want to write to and the new value, let's say 7. Nothing happens, but now if I read from it, I get the 7. So far so good. So it's a mutable variable in Haskell. And it's, normally we don't use, don't have mutation. Mutation is an IO, but if you really want to, you have that. And now this question with the can store computations. So for example, I can now do write IORef v7 3 divided by 0, and not 7, sorry. So I'm writing to this mutable variable now 3 divided by 0. And if I evaluate 3 divided by 0, then that would be an exception error, because division by 0. But I don't get an error. And that's this remark. So this cell cannot just have fully evaluated values like numbers. It can have basically these thungs, what in Haskell we call thungs, these unevaluated. So it's lazy. The cell is basically lazy. So it will only evaluate what I put in there if I actually need to evaluate it. So if I now do read IO ref v, then I suddenly get the exception. Because the read, the read would also not give me the exception, but GHDI wants to show the result. And in order to show the result, it has to evaluate the int, and then it crashes because I'm dividing by 0. So that's this remark that it can store thunks. Then there is modify IOREF. Okay, that's in the library, I think. So given such a reference cell and a function, it will do the obvious thing. I mean, it applies the function to the value, and I mean, that is then the new value. So let me put 7 back in, and now I can do modify IOREF v whatever times 2. And now if I read, I get it, I mean, it's 14. So modify IOREF applies the function to the value and updates it like that. Okay, demonstrated this. Demonstrated that. Okay, and there's also a strict version. So I mean, the signature is exactly the same as for modifier IOREF. That's another convention in Haskell, naming that a quote at the end, a single tick, normally means strict. We saw that already with fold left and fold left prime. So modify IOREF prime is a strict version of this. And this uses this operator, this $! Exclamation mark. When we talked about fold left prime, we mentioned bank patterns that force evaluation of the argument before the thing continues. So there is this, somewhere in the libraries, is this $! Exclamation point. So it's like the normal $. I mean, the behavior in principle is like the normal $. The only difference is that it evaluates its argument before it applies the function. And so the implementation of modify IOREF prime is it reads the old value and then uses this $! Exclamation mark to evaluate the new value before it puts it back in. So the only difference is that it first evaluates before it updates. So that should work exactly the same normally. So if we modify again multiplying by 2, and use this prime version now it should be 28. But if I modify by dividing by 0, then it immediately crashes. So that's the difference between the unprimed version and the primed version. So the primed version immediately runs into this error because it immediately tries to evaluate this. And I mean, that's one thing I haven't mentioned before. Maybe now is the time. What does evaluation actually mean? So it probably doesn't mean what you think it means. It doesn't mean that everything is fully evaluated. So in Haskell, when we talk about strict, for example, the seek operator, evaluation in that sense, or forcing evaluation, it doesn't mean that it's like everything is evaluated. It just means it's evaluated so-called weak head normal form. And roughly that means it's the outermost constructor. So for example, a list has two constructors, empty list or nil and cons. And if I have a thunk that's a list and I force evaluation, for example, with seek or with a bank pattern, then it will evaluate it until it knows which of the two constructors it is, whether it's nil or cons. But it won't evaluate, for example, the tail or the head. So it will just know it's this or that. Or for example, in the case of either, if I force an either, then it will know whether it's a left or right, but it won't know anything about the arguments actually. So then I have to force it again. So it's basically only the first step. I mean, a Haskell value is like constructor applied to, and the arguments again have constructors. So it basically just gives you the first constructor, the outermost constructor. And if you want to do more, then you have to force the arguments of the constructor and so on. In the case of numbers, it's sort of different. Because they are like built in. So if you force an int, then you really have the whole int, not just the first bit or something. But for like algebraic data types, it doesn't go all the way. I mean, if you have a tree, it would only tell you, in our case, it would only tell you this is a leaf or it's a node, but it wouldn't evaluate everything. Anyway, but in this case, division by 0, we see the effect like this.
Related to that, I think last week you mentioned that main is the only thing that is executed.
Yes.
I believe yes is well written.
Mm-hmm.
So I didn't get to ask, it like there's a runtime where everything else is put and it's just one is that come out? How does that work? How come all the other things are not executed?
So how thumbs work, basically, I think.
Right. I mean, first of all, I said only main executes, but I said also GHCI executes. So this is now like main. Yeah, thunks, I mean, you can think of, I mean, it's basically just yeah, it's an unevaluated computation, but you can think of it as a piece of code that will eventually give you a result in weak hat normal form. So for numbers, it will compute the number. So it's basically, I mean, in Haskell, an int, for example, is not like a 64-bit thing. I mean, it can either be that, like an evaluated int, or it can be a pointer to some machine assembly code that when executed will calculate this number. And then the first time, I mean, so, and in the beginning, basically, it's just, I mean, so in principle, you can think it's, I don't know how it's actually implemented, but you can think it's like either, I mean, like int could be a pointer or like 64 bits. And in the beginning, if you somehow do something, whatever, then it's a pointer to a piece of code that will actually evaluate that int. And if you pass this int around or use it in other computations, I mean, this is never triggered, so it's happily unevaluated. But at some point, you need the value of this int. For example, if in some code, I mean, you have an if, whether if this int is 0, then do this or do that. So at that point, you need to know whether it's 0 or not. So at that point, this pointer, I mean, the code would be executed, and you get an int as a result, and then you would store that in these 64 bits in the int. So the next time you look at that int, you don't have to execute it again, it would already be there. So you basically only calculate it once. Once you have calculated once, it's there. But I mean, yeah, there's a name for it. It's not lazy. It's called by need, evaluation by need or something.
Right? Yes.
So I mean, lazy, like pure laziness would mean that you each time have to calculate it again. But in Haskell you don't. So Haskell is optimized so that you only do it once, basically.
Eager evaluation
Eager is the other one, the strict.
is fully strict.
Yeah, that's no. And then there's lazy, but there's call by name, call by value, and call by need, I think. Call by value is the usual one. That's when everything gets immediately evaluated. Call by name is totally lazy. And call by need is you do it the first time, but then once you have it, you store it, you cache it basically. And then you don't need to do it again. So yeah, that's how it works basically. There are also, I mean, we talk about that maybe later this week when we talk about data structures or next. So there are also ways in Haskell to have like an actual int, I mean evaluated int, where it's guaranteed that it's evaluated. But that's like more primitive operations. Okay, more questions to this? Yeah?
If you're going around like things as a way, like what's the performance implications of that? Do they take up space? Do they?
Yeah, I mean, we had this example of summing a list where it used an insane amount of memory if I wanted to sum, like, I mean, for example, if you use fold L without the prime, then the memory goes up. And that's exactly that, because the thunk gets bigger and bigger. Because basically the thunk contains all the elements. I mean, for each element of, if you have 1 million elements you want to add, and if you don't use seek or bank pattern in between to evaluate the accumulator while you're going, then it builds up and up. So, I mean, this thunk is then basically there's one step for all the 1 million elements in the list, and it's like a huge thing. And that's basically a memory leak. So yes, I mean, that's one of the disadvantages of laziness, that you must be careful about this. That can happen. I mean, normally it doesn't, but I mean, there are like certain situations where it does.
And in those cases, you can profile the program and look for the.
Yes, there are profiling tools where you see which function allocates memory and how much is allocated, and then normally I mean, by like placing some strategic banks somewhere or seeks, then you can fix that. So it makes it more difficult to to avoid space leaks in Haskell. Right. Other questions? Okay, let's see whether there's. Okay, so we had this. Now let's write another example program. Or just. Okay, so maybe I should. Or maybe not. I don't know. Should we have a break now? Maybe? Yeah, let's have a short break. And then let's talk about problems with this. I mean, so far with this mutable cell, it had nothing to do with threads. But now, I mean, the main topic is concurrency, and we want to see what happens if you try to use IO refs. I mean, if this is now a way, of course, for threads to communicate. If both threads are aware of this IO ref, then they could like write and read from the same shared memory, and that's a way for them to exchange information. But it's like problematic because of race conditions and so on. So let's talk about that next after the short break. Okay, should we continue? So let me implement this. And I think I instead of overwriting the existing example, let me maybe create a new executable for this. I don't know, maybe IORef. Okay. Okay, let me copy this quickly. So this thread function is with what each of our 10 threads will do concurrently. So it gets an IORef and an int, and it will forever write its int to the given IORef and then immediately read again. And if what it writes and what it reads are not the same, it will print it to the screen. So let's see. So thread, so it takes an IORef int and an int, the IOA, var n forever. I'm just checking, is there a delay? No, okay. Okay, I need to import this data IORef again. So it writes IORef to the given mutable variable, its own integer, and then it will immediately read from it again. And when we learned about when yesterday, let me import control monad. So when x unexpectedly is not n, print, what was it? Doesn't matter, but x, comma n. Okay, and in the main program, I will create this IORef, new IORef, start with 0, then I fork my threads for 1 to 10, and then I wait 5 seconds. Fork var, sorry. One remark that I just thought of, I mean, sometimes, I mean, especially when you deal with blockchain and cryptocurrency, you often have like insanely many zeros, and it always confuses me. So it would be nice if one could write it like this. And indeed you can. There is a language extension called numeric underscores, which allows you to write this like that. I like this. So what will this do? So the main thread, the main program creates one mutable reference and then passes it to all the threads, to 10 threads. So we will have 10 threads. They all share the same variable, but have a different n. So n is from 1 to 10. On each thread concurrently will all the time, forever, write to this reference cell and immediately read from it again. And if what it wrote is not what it read, then it will print to the screen. And if we do this, for 5 seconds, then we see that that happens a lot. So it happens a lot that obviously some other thread between here and here, between the writing and the reading, modified it and wrote something else in there. So it's I mean, because the threads are threaded, I mean this one can be in control, or even right, in this case, I'm even running it maybe on multiple cores, so it can really be in parallel. But even if I didn't, it could still happen. I mean, we could try that out, what happens if I run single-threaded. Yes, N1, I think. Is it minus N1 then? Or I could just remove the threaded stuff completely. So it's single-threaded. Let's see. I'm not sure what happens. No. But it could have happened, right? Even so.
Yes.
Theoretically, yes.
You have to try a couple of times.
But but even if I do it on like two cores, then it happens. Maybe not as often as before, but it does. Right. So that's that's just the nature of concurrency, of parallelism, that it's very difficult. I mean, the threads can be interwoven in like unpredictable ways. So you have no guarantee that between, in our example, that between this line and this line, between 9 and 10, another thread can't basically write to the mess with this variable at the same time. I mean, that's how concurrency is. Well, there is one function, atomic modify IO ref prime. So that, let me just look at the example. There is none. Okay. Right. So atomic modify IO ref gets a reference cell and then a function from A to A comma B, and what it will do is it will, read from the reference cell, then apply the function to the value it read. It will get a pair of an A and a B, then it will write the first component of that pair back into the cell and return the second component of the pair. And it's called atomic because it's guaranteed that while it's doing this, it won't be interrupted by another thread. So, there's no example in the slides, but I think if I change this now to atomic, IO ref prime var function given an A. So I want to ignore the A and write my N and return it. Of course, what's the question? What's the problem there? A const, maybe. If I do it like this, then this should not happen, hopefully. Right. So, the difference with this atomic is, as I said, so you can do this, you can read up and update in one atomic step and no other thread can interfere. So that's good. So this is what I explained. Oh yeah, and it has this prime, so it will also force the A, so the new value. And that's good. And that means if you only have a single IO ref, then you can basically use that like to safely work, share it with different threads. Because it can't happen that in the middle between reading and writing, somebody else writes to it. So you can make sure that the value is always consistent. But the problem is that as soon as you have more than one IO ref, that doesn't help you anymore. So then, each single, because you can't guarantee using any of the functions in IORef, in data.ioref, that basically the access to more than one variable is consistent. For that you need something else. So we looking at an example now. I'm not sure whether I should revert this so that it's maybe. Right, so we have our original example back. Right, so let's look at an example where, when we had this bank example before, we did it all purely in Haskell and all was good, no threads. But now let's use basically IO refs for balances of accounts. So let me implement this, let's say here. Or maybe I should, I don't know, maybe a new executable again. Sorry. Let's call it, I don't know, accounts. Okay, that's fine. Okay. So type account, just an IO ref int. Okay, and now we transfer, oh yeah, and then it's your turn again. But let me write the signature. Transfer, count, int, oh. Right, so the idea is that that will, for the given amount, modify the first account and subtract the amount, and modify the second account and increment it. And okay, on the slides it's integer, maybe I should also use integer. Sure it matters, but right, and then we should be able in GHCI to do this. So if we create two accounts, one with a balance of 1,000 and one with a balance of 2,000, and then call this transfer function of 100, and then read the accounts, then the one should have the 100 subtracted, and the second one should have the 100 added. So maybe you can give that a shot for 5 minutes. Okay, maybe should continue. So, anybody have a suggestion? Sorry? Yeah, I got to do.
A new variable?
Combined the result of greater IOR from to old from. Like combined the result of read IOR
Uh-huh.
to
You combine the result of read.
bind.
Bind. Read a
Oh,
bind it.
okay. Sorry. Old from to or from? Or doesn't matter. From, yeah. Okay. Yeah, sorry. Okay. Okay. Yeah, and then I assume the same for. Like so? Right. Any comments? I mean, first of all, of course, if we don't have to worry about threading, that would be okay. There was this test here. Let me just, Cabal, REPL, what did I call it, accounts. So there was this example. So if we have A1, A2, map new IO ref, and we start with 1000 and 2000. And I must say that it's integers. Yeah. And then I try this now. And now I do map read IO ref A1, A2. Yeah, so that works. Okay. Of course, now the point I'm going to make soon is what happens if I do transfers in parallel from multiple threads. So with that in mind, is there anything one could improve here? Thinking of the primitives I showed you about IO refs earlier. Or maybe not primitives, but yeah, I think it's primitive. I mean, if you think about it, if two threads simultaneously do a transfer that involves like maybe one or two of the same accounts, I mean, then all sorts of interweavings can happen. And in this case, I mean, for example, between I read the old from and I write to from, another thread could interfere with from. So, I mean, I think we should definitely use this atomically modify IO ref that we saw earlier. So to at least do the write and read from each account atomically. I mean, so like this. Actually, I don't know whether on the slides it's like that. Or on the slides there is no solution. Okay, fine. Okay. So, I mean, I would probably do it atomically modify IO ref prime. Was it called like this? Let's just check. Atomic, sorry. Atomic. And how was that? It takes, so let's say from, and now it takes, it gets the old amount, so old from, and must return the new amount and the return value. In this case, I'm not interested in the return value, so I can just do old from minus amount unit. And I can do the same for 2. Right. Let's see whether I still, if I transfer 100, okay. So I do this again. So this also works. So this is a bit better now. Because now, while I modify the from and while I modify the to, nobody can interfere with it. So at least I'm guaranteed that while I'm in control, I mean the from will go down. But I mean I'm not. I mean yours is. I mean this is still bad, as we will see now. Okay. So yours is fine. IORFs are just not the right tool for this, because now we have many. And now to demonstrate that, let's see. So the idea is we generate 2 accounts, and then we will 100,000 times do a random transfer. Let me just see. Okay, so there's lots of new stuff. First of all, random. So I mean, the idea is we want to do stress test this and create some example accounts and then randomly do transactions like 100,000 in parallel and see whether this will work. In the sense, okay, we come to that. And in order to do random transfers, I need to have randomness, and we haven't had that. I think if you did the I/O exercises, then you have seen that already, but probably most of you haven't done that. So that's in system random. Let me see, random package. Okay. And I think I need to, or I know I need to put that into my dependencies. So apart from base, I need random. Let me reload there. And let me reload here, because I changed the dependencies, then I have to reload GHCI. And now I can import system.random, reload. Now I should have this random RIO. So this monad IO you can ignore, you can think of IO. So M can be IO. And this random A, we have seen that when we talked about quick check briefly. So that's a class for types. Type is an instance if we know how to generate a random something. So for example, int is, and then there is, this random library is not just in I/O, it also has pure randomness. You give it a seed, and then deterministically it will use this seed to generate pseudo-random numbers. But there are also I/O versions, and now we are in I/O anyway, so that's fine. So we can try this out, for example, random. And there's also without the R is for range. So if I want to generate in a range. So for example, I could do random RIO for ints from 1 to 6, and that would simulate a die throw. So I can do that. We saw this replicate M yesterday, but probably it's not in scope. Of course not. So let me import control monad. So now I have replicate M. Let's do 100 times random IO, random RIO 1 int 6. So now I would have 6 pseudo-random, 100 die throws. So that's this random RIO. It's not topic of today's lecture, but of course, nice to know that Haskell has support for random stuff. And okay, and the second thing I see on the slides is used, I think we also haven't seen that yet. If you have a list, you can get, there's an operator to get an element and a specific index. So for example, if I do Haskell, and that is exclamation point, exclamation point. It starts at 0, so this would be the H and whatever. 1 is the A and 2 is the S and so on. Of course, it's super inefficient because it's linear. So, I mean, if you index into a long list, then it takes, so there are there are also arrays in Haskell and so-called vectors that have constant time access indexing. But this is not the point. So, and with that, we can do this, this random transfer function. Okay. Let me do this now. So random transfer. So it gets a list of accounts and then does a random transfer. So I want to randomly select 2 accounts and an amount and then transfer it between those. So let's say first, and the index, because it starts at 0, is between 0 and length -1 of accounts. So max index is length accounts -1. So and then I can do, I use this random RIO for indices 0 and max index, and I do the same for 2. Do the same for 2. And then for amount, I know in the slides it's between -100 and 100. I find minus a bit silly. So let's do random RIO 1 and, 1 and 100. And then transfer from to amount. What did I do? Okay, let. I forgot the let. And what did I do now? Sorry. Yes, that's why this is just indices, but transfer expects accounts, of course. That's why I explained this exclamation point thing. So accounts from and accounts to. Right, so this should now do a random transfer, basically like on the slides. So it picks a random from, a random to, a random amount, and then invokes this transfer function. That was this exercise. Now we want to get the total value balance in all our accounts. So get total. So giving a list of accounts, IO integer. So get total accounts. Okay. So what do we need to do? We need to look up all the balances. So to look up one balance for one account would be just read IO ref. But now we have a list of accounts, so we must map over that, and it's effectful, so we use map m. So now in IO we have the list of all the balances, and now we want to sum this, but it's not, this here is not a list of integers, it's IO list of integers. Therefore we must fmap sum. So actually we can try this out. Let's go back to the terminal and reload. Let me do these, sorry. No, we can't. Let me do this again. So A1, A2, map M, new IO ref. what was the example? 1,000 and 2,000. Integer. Of course, bind. It's IO, sorry. Okay, and now I could try this get total for my A1 and A2. Yes, so 3,000. And I could also try a random transfer. A1, A2. And now map M read IO ref A1, A2. Okay, so it seems the random transfer was from the second one to the first, 11. So from was 1, 2 was 0, and amount was 11. I'm not sure, maybe I should, I mean, this doesn't check that from and to are not the same, but it also doesn't matter. I mean, it's a bit silly, of course, to transfer. Maybe one could make it better and check that from and to are different. But that's also not the point. Okay, and now the idea is, I mean, what do I expect? Or no, not what would one expect, I mean, of a bank? One would expect that money doesn't disappear. So especially, I mean, in particular, if the only transfers are internal transfers. So you have these accounts, and people are transferring between these accounts, but I mean, the money should never disappear. So the total sum of money in the system should always be the same. I mean, if you transfer from one person to another, then, I mean, those two people's balances change, but the total value doesn't change. And the idea is now to write a basically test program whether this invariant holds. So let me check the main program. So the idea is we just generate two accounts. We get the total value, which should be 3,500. And then we fork this monitor. I must look at this monitor. Okay, we do this monitor thing. Right. So the monitor is supposed to run in a thread.
Opening brightness.
Stupid. So the monitor gets the expected total value and a list of accounts, and it basically permanently checks whether if we get total value, whether that adds up as expected. And if not, then it says what we expected and what it actually does. So let's do this. So monitor. So it gets the expected total amount and a list of accounts, and runs forever. So monitor expected accounts forever do. So it actual, it uses this get total function that we defined. Why do I? Okay. And then when actual is not what we expected, then it screams. Okay, and I need to import control Onat again for these. Right. So this will permanently, does it on the slides? Just checking whether, no. It will just permanently sum up the balances in the accounts and check whether that always stays the same. Okay, now I think we have all our ingredients for the main function. So we create just 2 accounts. I mean, we could, of course, do more. Just, it doesn't matter, of course, but let's do the same. So 1,000 and 2,500 in the beginning. And then we get the total with our get total printed. Get total accounts. Now we fork this monitor. Monitor, so expected is the total we have in the beginning with our accounts. And we can use void again because we don't care about the thread ID. And now we do 100,000 random transfers in parallel. Just do this extension again. Random transfer accounts. And we wait 5 seconds. Just, I mean, this on the slide it says horrible. So of course there are better ways to wait until the threads are all done with their random transfer. But this is just quick and dirty. So 5 seconds should be enough for 100,000 head script threads in parallel to do this random transfer. Okay, and now hopefully we get like something. So let's see. Cabal run accounts. Okay, good. At least once. Let's try it again. Okay, this time nothing happened. Let's try it again. Maybe I should do more. So it doesn't happen very often, it seems. But I also, let me change this here again. I had 2 threads, 2 cores. Let's use all my cores. Maybe then it happens more frequently. At least in the very first example. Okay, yeah, okay. Wow. Okay. So we see the more parallel it is, the more often this invariant is broken. That instead of 3,500, we have a different amount of money in our system. And the reason, of course, is if we look at the transfer function, I mean, this is atomic. I mean, each line 12 and 13 are atomically, so nothing can, no other thread can interfere there. But between line 12 and 13, another thread can interfere. For example, our monitor can check the total while when we have already subtracted the amount from the one account, but not yet added it to another account. And that's why we see sometimes this, that suddenly money seems to have disappeared because it's basically in transit. I mean, actually banks do that as well, that money, which is one of the reasons we're sitting here and doing blockchain. But yeah, so the point is that like an invariant, I mean, it would be nice if that was unobservable, right? That no matter how the threads are interwoven, it will never, I mean, it should be invariant. A transaction, I mean, it's called database transaction for a reason. I mean, financial transaction should also be like that. So a financial transaction should be atomic in the sense that, I mean, you can observe like the old state, and then the transaction is atomically, and then you see the new state. So where the money has gone from the one account and is on the other, but you should never be able to observe a state where it's gone from the one but not on the other. So in that sense, it should be transactional, atomic. So you shouldn't be able to squeeze between. And I mean, classically, if you were now supposed to implement this, you would probably reach for something like a lock. So, I mean, if you do a transfer, you first acquire some sort of lock and then do the transfer and release it again. But that, I mean, if you do that too roughly, I mean, if, for example, there's only one lock, one global lock, then it would work, but then it wouldn't be concurrent anymore. So then you couldn't do concurrent transfers. If each account has its own lock, then you would need to acquire a lock for the from and to, and that is then deadlock. I mean, that can happen because you wait for, I mean, if it's 3 accounts, A, B, C, I want to transfer from A to B, let's say. Right, and somebody else wants to, it can be 2, I think. So I want to transfer from A to B, and somebody else wants to transfer from B to A. And if I use locks, which do exist in Haskell, then I would first like acquire the lock for A and for B, and then do my transfer and release them again. And the other one simultaneously tries to acquire for B and for A and would release again. And then it can happen, so I acquire the lock for A, but before I can acquire the lock for B, the other one has acquired the lock for B. So I'm waiting for the lock for B and he's waiting for A, and we deadlock. So with locks, one always has to be very careful with deadlocks, and there will be an exercise for this in week 2 to demonstrate that. There are ways around that if one orders the locks in some way. So for example, sorts the accounts by some sort of account number and then always acquires the locks in the right order, in the same order, then one can avoid it. So it's possible to somehow fix this with locks. But it's complicated and lots of things can go wrong and you can end up in deadlocks and so on. And Haskell, I don't know, I think it's not today, but let me just check quickly. Oh no, right. Yes, it's just mentioned. Just for two. Okay. Yeah, so there is, I mean, there in the slides there is not much to, so there is something called mvars in Haskell. I'm not sure what M means. Mutable. Maybe mutable. So this is a bit like an IOREF, but for IOREF, I mean, there's always a value inside. These mvars, you can think of them like boxes that can be empty or full. And there's, I mean, the fundamental operations on mvars are take and put, and that behaves as follows. So take, if the box is full, it takes the value out. So it empties it, but you know what value was in there. If the box, however, is empty, it blocks. So the thread blocks until somebody else puts a value into the, and then you get it. And put is like dual. So if the box is empty, you put your value in and done. But if it's full, your thread blocks until somebody takes it out. And so this is actually a very cool abstraction, very beautiful as well. And has like fairness guarantees. So if several threads wait to take, then it's guaranteed that each of them at some point will get its turn and so on. And if you just use mvar of unit, so you don't care about the value, just whether it's empty or not, then that's basically a classical lock. So you can implement a classical lock in Haskell using mvars unit. And I think there will also be exercises to that, this philosopher stuff. And that's nice, and I mean, I personally use them a lot. I think they're quite cool. But I mean, they have all the problems I just mentioned with deadlocks. So once you use mvars and you're not careful, and there are several mvars, then it can happen that threads deadlock on each other because each is waiting on the other. Right. And instead, there is something called software transactional memory in Haskell, where you basically don't have to worry about deadlock. So it's a beautiful abstraction, and I know Clojure has it, but I don't know about other programming languages that have that. So that's really cool. So the idea is basically it's transactional. You do your things, can involve several vars, and then either it succeeds and then or not, and then you retry to do it again. And it's intelligent, it will only retry if it has reason to believe that the situation has changed somehow. There are slides, yes. So, and that's in the so-called STM package for software transactional memory. So there's something like transaction, so it's a monad, the STM monad. It's a lot like, you can think of it like a restricted version of I/O. So basically I/O which can only read and write variables. So it can't do like write something to the screen or do networking. It can basically only do what we saw earlier with IOREF. So it can modify variables. And so you do your things in a monad, and then you can run these monadic things atomically. So you are guaranteed that it will not be observable some intermediate state. And yes, and it's easy to compose as well. So even if you get this right with the transfer, if you somehow make that atomically, then it's, for example, I mean, there are examples, if you do two transfers or something, if you want to compose transfer into something, then it's again difficult to do that with logs. So even if you have something that's transactional, compositionality is not given, whereas in software transactional memory, it just works. Okay. And let's look at the interface so that hopefully, I mean, it is very much like for IOREF, except now instead of IOREF, it's called TIVA for transactional variable. So TIVA is what until now was IOREF. And there is this monad STM, software transactional memory. So as before, we can create a new variable. Now it's not in IO anymore, it's in STM. There's also a version that does it in IO. We can read and we can write. So this is exactly like before with IOREFs, except now it's in STM and not in IO. And then crucially, you can run it in IO. So once you have your computation, you can atomically run it in IO. So it's really like a restricted form of IO. Like IO, which only has new IOREF, write IOREF, and read IOREF. And okay, and there's also a helper function modify TIVA, which we could also implement ourselves. So same as modify IOREF. So it reads and then writes the function applied to it. So let's, I don't know, probably I should call it account STM or something. So let's try to modify our example accordingly. Let me just copy this, copy app IOREF, no, it was accounts. It's called STM. And let me copy this here as well. So create a new executable. Let's call it accounts STM. Accounts STM. And I need STM as a dependency. Let's reload. We closed all this fluff. Okay, let's see. So now we will change our account type. So instead of IOREF integer, it will now be TIVA integer. So I need to import this, of course. And now transfer will be in STM. So instead of IO, it's in STM. But I mean, it's in principle quite similar. So it's now modify TIVA. I could also use the strict version. In the slides, it's not, but doesn't matter, I suppose. So the from with minus amount and modify TIVA to plus amount. This is again, this is this prefix minus sign problem. Okay, and so that's that. So it's very similar to IOREFs. I did it with this atomically modifier IOREF before, but I also could have done it with modifier IOREF. And instead of modifier IOREF, now I'm using modify TIVA. So basically the only difference now is that instead of IOREFs, I'm using TIVAs, and instead of IO, I'm in STM. But the code looks very similar. Right, so that's that. Right, so I must modify this get total, which is also simple. So instead of an IO integer, it's now an STM integer. And the only thing I need to change here is instead of read IOREF, it's read TIVA, because now the accounts are TIVAs. See with the random transfer. Right. So the random transfer stays in IO. So this random number stuff is still IO. But now the transfer, as we know, lives in STM, so this doesn't type check. But we already saw on the slide how I can execute such an STM computation in IO with this atomically keyword. So this is random transfer. And monitor, I suppose. Right. Right, so in monitor, the only change is that, again, this get total is now an STM. So in order to do it in IO, I also need atomically. The rest stays the same. And now in main, okay, here instead of new IOREF, it's new TIVA. And for get total, I need atomically. And I think everything else is the same. Oh yeah, new TIVA IO, sorry. Because I want that in IO. Okay, and now let's see. So this is the old version, just the old one again. So we get lots and lots and lots of violations where we observe less than 3,500. And now with STM, hopefully, yeah. Okay, so that works. That was just this, I don't need anymore. Okay, so right. So I just modified slightly this program, so I had to change IOREFs to TIVAs and do everything in STM, and then if I wanted an IO, I atomically do it. And now we do no longer observe this problem that we see in invalid state, because the crucial thing is this transfer function. So I now can simply do these things, one after the other. I subtract the one and add the other, and now it's guaranteed by the magic of STM that no thread will interfere between these two. But the cool thing is it's also not using locks. And actually it runs completely in parallel, and it can happen that another thread interferes here, but then basically this realizes that and just tries again. So it basically doesn't block. So what can possibly run in parallel does run in parallel, but if necessary, if it realizes that some TIVA has been modified by somebody else, then it retries this transaction. So maybe we should, let me just see what's the next topic.
So in theory, we could run out of resources, trying forever because it's always interrupted. That's the first thing one could think of, right? But in practice, it almost never happens. So it's just in theory, it could happen that computers nowadays, servers have so much resources that in practice, if you retry enough times, eventually you will get it. That was on the papers.
Mm-hmm. Right. Just want to see. What the example there is. Right. Okay, so there, I'm not sure whether. Okie dokie. So maybe we should have another break now, first. Well, it's a bit about join, and then it's retry, and or else, and then it's asynchronous.
We'll be going for a bit less than an hour.
Oh, okay, then let's continue a bit. Let's do this join thing still. Okay. So where were we? Right. So I mean, so that works beautifully. And as I said, STM, you can think of it as a restricted form of I/O. So one problem is, one feature is you can't do I/O in an STM. Other I/O except for these things. So what if you would like to do I/O? You can't. But one way that sometimes helps is instead of you can't perform the I/O, but you can like compute the action and then perform it outside. So as an example here, until now we also had like negative. We didn't check whether the transfer could actually be done. So sorry. So we can fix that. And let's say we want to like log a message depending on whether it worked or not. So one way to do that is that instead of unit, we return now something of type IO, like an IO action. So this, it's important. This is, I think, quite a silly example, but the important point here is that IO or STM or anything else is all first-class values in Haskell. You can't just return ints or strings from functions. You can also return IO actions. So this is now an STM transaction that returns an IO action. And so in this example, so we check whether this person has enough. So let's say old from read tiva from, and if old from is less than the amount, then we want to return the IO action that prints an error message basically. So we can say pure put string line not okay. Sorry, then of course. Sorry, I was in the when world. Yeah, doesn't matter, I can leave it like that. And pure is that like on the slides? Let me just check. The amount. Okay. Let me just do it like on the slides. That's a bit silly because in this, the example is not very good. Because in this case, we could just as well return a string. I mean, whatever. But this is just to demonstrate that I/O is a perfectly reasonable return value. So now we have, earlier our transfer function it just did stuff. I mean, it did the transfer, but it didn't return a value. Now it returns this I/O action, which is like a logging action. So now in our random transfer, this is now we get this I/O action, and therefore I get a warning. Right. Because now, so let's call that, I don't know, action. And now I can actually perform the action by performing it. Now it probably tells me to join. Yes. Okay. Now we can try this out. Although this will take a while because it's like 100,000 times. So maybe I should, oh yeah, after 5 seconds it stops. So it always only takes 5 seconds. So it's fine. Somewhere there was a not okay, I think. But that's also not the point. Yes, so this is actually, so this is not about STM or anything. It's more about monads or Haskell in general, because that probably for beginners looks strange, a type like this. So it's a computation in the STM monad, and the return value, the final result of that computation, is a computation in another monad. But there's nothing special about I/O or STM in that regard. I mean, you can pass around values, you can have them in lists, you can have them as leaves in trees, you can use them anywhere. So now so instead of not returning anything, we return an I/O action in this transfer function, and then we use it, here. So we bind action against the result. So action is now an I/O action, and therefore if in the next line we write action, we actually execute that action that this function returned. So now if the transfer would have failed, we get this, it will print not okay, and if it succeeds, it prints okay and the amount. And as you already see here, there is this warning, and if I follow this suggestion, it tells me to use join. And if we ask for the type of join, we can't because we are not in the REPL. Probably in control monad. Right. So this is another useful function that could have been on the slide yesterday with all the useful monad functions. It's called join, and it basically collapses two layers of the same monad into one. And so, for example, if you have I/O of int, you can turn it into an I/O int. So in this case, that was exactly that. So atomically, because the return type was I/O unit, this thing here was I/O of I/O unit, and now join flaps it together to one I/O unit, which we can execute. Right. And incidentally, but that's more for the category theorists among you, instead of bind to define a monad, one could also use join. So join is as powerful as bind. If you have join, I mean, you can define bind in terms of join and join in terms of bind. But that's not of practical importance, just theoretical interest, because join is somehow prettier. I mean, it's simpler mathematically. Bind is more useful for programming, but join, I mean, has a much simpler structure somehow. Anyway, not important. So we have this, did that, did this. Okay, and the next, I mean, this is already very useful, but there are two more important operators in STM. One is retry, and one is or else. So retry will stop the execution of some STM transaction and start it over at the beginning of the transaction you're currently doing, which is also interesting. So if you have like two, I mean, it will know, I mean, it basically starts the whole atomic block again. That, yeah, so it's not a lexical thing. It's, and the or else will do the first thing, and if that goes through, that will be it. But if the first one hits a retry, it will instead, I mean, will not retry the first one, but will instead do the second one. And the cool thing also about the retry is it's not like an eager retry, so it won't immediately do it. It will only do it if it has a chance of succeeding this time. So if nothing has changed, so somehow the system monitors, I mean, STM computation can only, because it's very restricted version of I/O, it can only, I mean, whatever happens depends on the values of certain T-vars. So if the logic leads it to a retry, that was because certain T-vars had certain values. And a retry would lead to the same result again if the T-vars didn't change their values. So the retry won't do anything until somebody somewhere changes one of the T-vars. Only then does it retry, because only then is there a chance that now it doesn't need to retry. And so, for example, we could change our transfer again to so I mean, now when the person didn't have sufficient funds, we failed basically. We didn't do the transfer. So alternatively, we can use retry. So this will now basically block or wait until somebody else gives him money, and then the transfer will go through. So we can try this random transfer. Sorry, not random transfer, transfer. So in this case, until now we just stopped, but instead we can say do the retry thing. Okay. And I would actually like to try this let me see. Let me just try to, what was that called? Accounts STM. Right. I'm not actually myself not sure what will happen, but let's see. Right. Sorry. Let's just create 3 accounts this time. So A1, A2, A3. Map M. New T-var IO. Let's say 1,000, 2,000, 3,000. Okay. And now let's see what happens if I do atomically. Atomically transfer from A1 to A2, 1,500. Okay, now I have a problem because it's, I mean, I can't, because it's in GHDI. So let me just, I should fork this. So let me fork this. Right. So now I have forked a thread that wants to transfer 1,500 from A1 to A2. And we see it's blocking. So that is because, I mean, there are not sufficient funds. So it does the retry. but nothing changes. I mean, none of the accounts have changed, so it doesn't even retry. The thread is just sleeping and waiting. And now hopefully if I now send funds from somewhere else, that one will go through. So let's try join atomically transfer A3, A1, 600. Yes. So it's a bit garbled because that's also a thing. I mean, now I have two threads, the main thread and this forked one, and they both try to write to the console, and the console is not, I mean, there is no lock on the console. So it can happen that the output is like joined from the two. But let's see. So here I did this, and then, okay, yeah, it's not this bad actually. So this was okay. So A3 sent to A1, and then the retry actually did retry because he realized that something changed. So now A1 has 1,600, and now the transfer went through. In between the GHCI, I mean, it wanted to write, okay, 1,500, but in between the GHCI main thread wrote its prompt, so therefore it looks a bit weird. But now if we do map, no, atomically map M read TIVA A1, A2, A3. So now, I mean, so the last one sent 600 to the first one, who then, now it was unblocked and sent 1,500 to the second one. So it's really cool. Yes, so that's a demonstration of this retry. Okay, so maybe now we should have a break. 10 minutes.
Questions?
Yeah, sure. Questions?
How does the runtime know what a retry is?
I have no idea, but there's an excellent, or there are several,
Has a talk about it?
really? Because there's an excellent article by Simon Peyton Jones about this.
Yes, as well.
When
We
we-
share it. Maybe.
Yes, we should share it. So there's a beautiful article with elves and Christmas and Father Christmas, I think, about SDM, which explains how it works, I think. It's really cool. Other questions? What are you again? Okay. So we saw retry in action. Why is this? Okay. Now that I have this extension, it seems it wants me to use it. Anyway. Right. So we saw a retry in action, so that blocks until some of the condition changes, and then finally it can go through. Now there was also this or else, and that will also be a nice example for this compositionality that I mentioned. So let's write a version of transfer that takes 3 accounts. So the idea is, just reformat this, it fits. Okay, so the idea is that we have basically 2 from accounts, and it should transfer from to 2, but if there are insufficient funds on from, it should instead use from prime. And this is now super simple because we have transfer already. So we can just do transfer from to, amount, or else transfer from prime to amount. So I mean, I have my transfer, and in the way it's written now, it will block if there are insufficient funds. And we saw if I just use transfer like this, the thread actually blocks. But now if I combine it with or else with this other transfer, if there are sufficient funds, it will just go through. But if there are insufficient funds, it will not block. Instead, it will try the next thing. And only if there are also insufficient funds there, then the whole thing will block. So let's just see whether that works. Let me reload. And let me create accounts again. Okay. And let me demonstrate again. So if I do this atomically, transfer the other one, this one. So if I try to transfer with the normal transfer from A1 to A2, 1500, it just blocks because there are insufficient funds and nothing changes, so it blocks, so I have to interrupt it. But if instead I now use this transfer prime and give A3 as an alternative from, then it just goes through. And if I now check, sorry, which one? The one where I read to check this one. So we see the first, I mean, even though it tried first from the first account, there were insufficient funds. So then it tried the alternative, the 3,000. There are sufficient funds, so it subtracted the 1,500 from the last one and added it to the second one. And this is sort of beautiful. So, I mean, you have this transfer, which is now transactional, and you can compose it. So you can, as in this transfer prime, I just used transfer. And good luck trying this with logs in a different programming language. I mean, even if you get transfer to work like this, it's almost impossible to then use that transfer and because then it will just block. So I mean, if you implement transfer in Java and get it right, so it's transactional and everything, you use fancy logs, and implement this thing that it will block until there are sufficient funds, then you can't, there's no way to use that twice to implement something like transfer prime, because then it will just block. And it won't realize that it's like invoked in a bigger context and there's now an alternative that it's supposed to try. So this is really very nice. And I think Robertino shared this paper by Simon Peyton-Jones that hopefully explains it for those of you who are interested. Okay, let's go back to the slides. Okay, and next, last chapter. So there, I mean, was this comment on the slide horrible? And the problem is, I mean, the point is, I mean, what they try to achieve is, I mean, we are forking 100,000 threads that do these random transfers. And the idea was just we want to wait until all those 100,000 transfers have gone through. So we just waited for 5 seconds. But of course, what we really would want to do is wait until the last transfer went through and then immediately stop. But it's not so easy to do this. I mean, not obvious at least, or not completely trivial. And I mean, these Haskell threads are, so the philosophy of them is that they are as simple as possible, and that you just, if you want something fancy, then you build it yourself on top of it. So the threads themselves are super lightweight. So there is no built-in mechanism to wait, I mean, to somehow signal to the main thread that they are done. But with everything we have learned, I mean, one could implement it by hand. Okay. So we could do this with Tiva. So here's explained how. So we could use a Tiva bool to indicate whether a thread is finished. So in the beginning, all of them are false. And once a thread is done, we set it to true. And in the main, we basically check whether all of them are true. And so actually, we could try this, I suppose. I mean, here it's not done, but I think it's a good exercise to try it. So let's do this just. So let me see whether I can. I just think this will now take forever because now we have this. Probably I should. Let me just remove this stupid I/O thing again. Sorry, yeah, I should, I think. Let's revert that back to what we did before, so without this stupid message in the end. Because that takes forever. If I have 100,000 lines on the screen, that will take forever. Right, and then this join goes away. What else? I think it's fine. Okay, and here the type is then, of course, also just. Okay, I hope this is now correct. Okay, fine. Let me just try it again. So it should now wait 5 seconds and then, okay. So this is like the old state of affairs. And then let me see whether I can manage to do this. So in the main thread, I need this, so I need a list of 100,000 Tivas that are initialized to bool, to false. So what would that be? Let's say, or B's or whatever. So replicate M 100,000 times. So what do I want to do 100,000 times? I want new Tiva IO false. So BS should then be a list, 100,000 Tivas in it, all initialized to false. Now, now I want to, so I must change this random transfer because now it must get a Tiva bool. Let me do this first. So it will get the counts, but it will also get a Tiva bool. Let's call it done. So I do the transfer, and after I do the transfer, I just write Tiva true, done true. And of course I could do this in the same transaction. Maybe I can, why not? Right. So so far so good. And now of course here I must somehow pass this. So instead of replicate, I will now do 4. So instead of doing 100,000 times the same, I now take this list like so. Okay, and now of course I must somehow in the main thread wait until all of them are done. So I can do, so I remove this horrible thread delay and do atomically. Let's see. So there's this all function. So first of all I must get all of them, the values. So so I do map m read tiva over bs. So let's call it xs. And there was this all function. And there's all and there's some other that I actually now want that checks whether end, it's called end. So that takes a list of booleans and says whether all of them are. So for example, I can do and true, 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 true would be true, but if one of them is false, it's false. Okay, so and is what I want. So if not and xs, then retry. Or actually, I can use unless, just for unless and xs, retry. And that's it. So this will now read all the values of the 100,000 booleans. And if all of them are true, it won't do anything. So the transaction will go through and we are done. But if one of them, at least one of them is false, it will retry. So this atomically should now block until all the 100,000 threads have written true into their boolean. I haven't tried that before, so I'm not sure it works, but let's see. And ideally, it's faster than 5 seconds now. Or maybe not, maybe it takes longer. Okay, it takes longer, so that means that before we were not waiting long enough, actually. But of course, it's no guarantee. I mean, maybe, oh, and it can also be that it now blocks forever because we have this thing that it retries if the transfer doesn't go through. That might be a problem now.
But shouldn't
Yeah, at some point it should.
try again, because it's going to, as soon as one fork finish and locks, it retries again, right?
No, but these 100,000 random transfers, it could be that one account simply doesn't have the funds.
Right.
So I think this is the problem. So I think I must revert it to the original version where we didn't do this retry here. So maybe we can just don't do anything in this case. So we just don't do the transaction. I mean, okay, let's try this one more time. Hopefully it was that. But should that take so long? But maybe because now each time it has to.
Evaluate the boolean. I mean, not all the.
Yeah, actually, maybe this with the booleans is actually stupid anyway. I mean, we have to every time scan 100,000 booleans.
Can you try?
I mean, it's just better to have a counter.
Can you try with 100? Just with 100 transactions.
Yeah, whether in principle it works. You mean? Yes. So let's try with 100. Yes, so that works. So it's just because somehow it takes forever. But I think this is anyway stupid with the booleans. I think what you should do is you create one new tiva IO, one tiva int, and then we forget about this, and just do replicate m underscore fork IO run done. And in random transfer, so it's now not a tiva bool, it's a tiva int. And I just modify tiva prime, done with +1. So now each thread has the same tiva and they just increment it when they are done. And now in the end, oh yeah, I must say how much now. Let's try first with 100. So now it's simpler. Let's try this. Sorry, did I do now? Did I now kill my thing? No, there it is. Okay. Okay, and now let's try it with 100,000. This should be much faster than with the booleans. Yeah, okay. Right, so the idea was now I have one tiva that is initialized to 0. Each of the 100,000 threads gets it, and when that thread is done, it increments it by 1. And in the main thread, I just block until I reach the number, and then I'm done. So I don't need this thread delay with 5 seconds. And it stops the moment it's done. Okay, but that's not on the slides anyway. Instead, the last chapter for today is this other interesting, nice package on Hackage. It's called async. So no, don't let me. Let's first read the slides. So async is like it gives you more higher level options than just using fork IO. And so the things there are in control, concurrent async. And so it basically, the async is an improved fork IO, which gives you back not a thread ID, but an async. It's called async, it's a type. And async is basically a computation that, like a box or so, and you can wait on it. So you can fork with async, and you get back a capital async. And then later, if you want, you can wait on that async, and then that thread will block until the one you forked returns a result, and then you will get that result. Right. Right. So we could use that. I'm not sure whether I should, maybe I should do another, copy this again. Otherwise we mess everything together. So copy app accounts STM to app accounts async, and let me change the cabal file accordingly. Okay, let's open this. Oh yeah, and sorry, of course I need to import this async library. Which hopefully won't take forever. Okay, now it's building this async library, but that didn't take too long. Right, and let me import control concurrent async. What was it? Accounts. Okay, fine. So now we should have this async available and the wait. Right, so in order to use this now, so I did this thing with the TIVA and this done. So let's remove this again. So we go back to our original version. So I remove this here. This done is, we are done with the done. So this should compile again. And now here. So now, I mean, earlier we had this underscore here, so we didn't care about the thread IDs. Now we replace fork.io with async. And now we do care about the asyncs. So asyncs. So now we have a bunch of asyncs. That should be fine. Just a second. Want to see whether this compiles now? Yeah. Yes. So now we have a list of async unit because our random transfer function has return type IO unit. And now we must wait on all of them. So now we can do map m wait asyncs. And that should, in principle, I mean, have the same effect as this version. Let's see again. So this was my solution using TIVAs to wait until all of them are done. It did work before, didn't it? Was it that long? Yeah, okay, fine. And now let's try with async. Oh, much faster. So somehow async is much faster in this case. Not really understand why, but
the library has to be optimized.
yes, probably also the problem is, I mean, all these 100,000 threads try to increment this TIVA at the same time, and then they all block on each other. I mean, they basically have to synchronously do this. So probably that's a huge overhead. In that regard, this original solution with the bools was maybe better, but then you have the problem that you always have to scan the whole list. So maybe if you used an array of TIVA booleans would be better, or whatever. But anyway, so this works. So it's like a beefed up version of fork.io, where you have the option to wait until the thread is finished and get the result. And this, I mean, there was this question earlier, how to synchronize the threads. That's one way. So you can wait in one thread until another thread is finished. But there are also like higher level functions in the async library. So for example, I mean, we had this replicate m, and there's like a concurrent version of it. So you can just do replicate concurrently, and basically has the same signature as replicate m, but then it won't do it sequentially, like the replicate M would. It will do it concurrently. And with the underscore version, if we are not interested in the results. So we could, instead of explicitly getting here these asyncs and then waiting on them, we could just use replicate concurrently underscore. And that should do exactly the same thing. Yes. And what else? Okay, I showed that already. And right. And we saw earlier with the server example, the shouting server example, that if I disconnected a client, the hget line resulted in an exception on that thread, and that thread died. But the main thread just happily continued. With async, if an exception is triggered in a thread, then it will be propagated to the parent thread if you do a wait. So if you wait on a thread and then that thread throws an exception, then the wait will throw an exception. So, I mean, whether that's what you want or not, of course, depends on the use case. But this is a way to detect whether there was an exception in a thread. Right, and so it just gives you more control. I mean, you can, of course, handle the exception in the thread, or you can handle the exception in the main thread, or you don't handle it at all, but at least now you get notified if there is an exception. And you can also, with this handle, this async A, instead of waiting for it, you can also cancel it. So it basically tries to kill the thread and then waits until that thread actually is killed. We haven't looked at that, but there's also, I mean, in I/O with this thread IDEO, there's also a kill thread. Right, and that's basically it. So, and you can have a look at this async chapter, package. Sync package. So that's very nice as well, I think. Right, and this Simon Marlowe is also one of the big names in Haskell. He has written a book about concurrent Haskell. He knows what he's talking about. Right, and there are, I mean, all sorts of nice things. And like more that, but here, for example, is this cancel that we talked about. And then there are also higher level things like raise. So you have two I/O computations, one that results in an A and one in a B. And what that will do is it will start them in threads, and then whoever finishes first, you will get the result. So if the first one finishes first, you will get a left A, and if the second one finishes first, you will get a right B, and the other one that didn't finish will be killed, cancelled. And this concurrently we saw, so we saw it for lists, so there's also a version for pairs. So you do these two things concurrently and wait for both results and then return the result as a pair. And I think we saw this for, replicate concurrently we saw. But there are also versions with map and for, and so basically all the things we saw now yesterday and on Friday, so map M and for M, which of course does it in sequence. So if you map an I/O action over a list of stuff, then it will execute all those I/O actions in sequence. And here in this async library, there are versions where instead it will do all those I/O actions in parallel, concurrently, and then somehow collect the results. So yes, that's async library is very nice. So yeah, that was the last slide. So what have we done? I mean, talked about briefly parallelism, concurrency, and saw the primitives in Haskell, so fork I/O basically. and that it's very lightweight, so you don't have to be afraid to start thousands of threads. Haskell can handle that. And the philosophy is to keep it as simple as possible, and then everything fancier, like these things as arrays and stuff, you can build on top of it in libraries. And then we looked at first threads in isolation with the server example. So we saw how to do a simple server in Haskell and a client for a server in Haskell. And where the threads were for each client that connected, we had a separate thread, and the threads were completely independent of each other. Because, I mean, there was also no database or no state, so they didn't need to communicate. And then we talked about how they can communicate. So first was IO refs, which is, just shared memory in Haskell, where several threads can access. But that's like insecure if they do it like simultaneously. So then we saw that this atomically modify IO ref, that at least if you only have one IO ref, that's basically sufficient. You can make that safe. But as soon as you have more than one, like with the bank accounts example, it's impossible just using IO refs to do this. And then the classical solution for that would be locking. And that's also possible in Haskell using mvars, which are also beautiful in Haskell. But, because that is relatively standard and you know locks probably, instead we looked at the software transactional memory, where without blocking, basically you can achieve composability and transactional behavior, even if it involves more than one of these T-bars. And finally, we looked at the async library briefly, which allows you it's a higher level than fork IO, because you can wait on threads and have these high-level combinators, like run a list of IO actions in parallel, for example. Are there any questions?
Can you create other threads being a thread?
Yes, a thread can create a thread. More questions? Okay, then I hope this today was like a nice change to yesterday. I think it's, of course, concurrency is a difficult topic as well, but it's like of a different caliber. So it's not so theoretical, it's more practical. So I hope it's a nice balance. Okay, then let's stop for today.